Polarization. The transverse electromagnetic wave is said to be polarized, more especially plane polarized in the y direction, which means that the alternating electric field vectors are parallel to this y direction for all points in the wave. Okay, we look at it from P point. E is oscillate along y direction. This is Z. This is Z. The magnetic field vector are parallel to Z direction, but we focus our attention on the electric field, to which most detectors of the electromagnetic radiation are sensitive. The plane defined by the direction of propagation, the x-axis, and the direction of a polarization, the y-axis, is called the plane of oscillation. The electromagnetic waves emitted by a television station all have the same polarization, but the electromagnetic wave emitted by any common sources of light, such as sun or bubble, are polarized randomly or unpolarized. Unpolarized, the electric field at any given point is always perpendicular to the direction of the travel of the waves, but changes directly randomly. You see, the E can change it randomly. This is the direction that the electromagnetic wave travels, okay, towards you. This is the E. Okay. Mathematically, we transfer unpolarized light into superposition of two polarized waves whose planes of oscillation are perpendicular to each other, but with a random phase difference between them. Now, we treat them as a two oscillation, okay? We'll see. Okay. And the phase difference between these two are random, so you can have this any of them, okay? Partially polarized, its field oscillations are not completely random, nor are they parallel to single axes. We draw one of the arrows of the double arrow representations longer than the others. This one is longer than the other one, so it looks like this direction. Okay. Other ways to produce a polarized light: by being reflected from a sheet of a glass or other dielectric materials. 2. By scattering light from atoms or molecules. Polarizer. Incident light wave is unpolarized. When we go through the polarized sheet, only vertical polarized light can pass, or along the axis of this polarization can pass. Components of electric field vector that are parallel to the polarizing direction are transmitted by a polarizing sheet. Components that are perpendicular to the polarized direction are absorbed by the sheet. When originally unpolarized light is sent through a polarizing sheet, the transmitted intensity is half of original intensity. Okay, because so half was absorbed, half passed. So the I is equal to half I0 intensity. Somewhat less than half intensity is actually transmitted by the real polarized sheets. Law of Malus. You see, if this is the polarized sheet, okay, with direction of its polarizer, and this is the E, okay, which can pass when they go through this polarized sheet, only this part can pass, and this part was absorbed. Since the intensity is proportional to E squared, So we find E vertical, EY equal to E cosine theta. Okay, and the intensity is the square. So the intensity passive one is about the original intensity times cosine square theta. This is the law of Malus. I equal to I0 cosine square theta. Theta is the angle of this E to the y-axis.
This device consists of a microwave emitter, a microwave receiver, and a bar graph whose length is proportional to the intensity of the microwaves picked up by the receiver. If we rotate the emitter 90 degrees, the intensity drops, then returns to its original value as the emitter is rotated another 90 degrees. If we now place a metal disc with slots in the path of the beam, the intensity of the beam is reduced, but the beam still passes through. If we rotate the disc 90 degrees, the beam no longer passes through the slotted disc. If the disc is rotated another 90 degrees, the beam passes through. This animation shows how the electric field vector of the microwaves is reduced as it passes through the slots. When we rotate the disc to this orientation, currents set up along the metal strips dissipate the energy of the electric field, and the microwave intensity is greatly reduced. These two sheets are examples of polarizing filters. Unpolarized light passing through the filters becomes polarized by selective removal of light with certain polarization directions. If the filters are placed on top of one another in this direction, the light passing through both filters is only slightly dimmer than the light passing through one filter. If we rotate one of the filters 90 degrees, very little light passes through the second filter. Light passes through these two polarizing filters when they are in this orientation, but not when one is rotated by 90 degrees. If we line them up again and flip one filter over, they are still lined up and the light passes through. These two polarizing sheets show the same effect when one is rotated. But when the top sheet is flipped, the light will not pass through. How is this pair of sheets different from the first pair? This animation shows the polarization axes for the first set of polarizing sheets, and how their relative orientation changes as the top sheet is first rotated, then flipped. Here are the polarization axes for the second set of sheets. When these polarizing sheets are in the proper orientation, light can pass through the first sheet, but not the second. If we insert a third polarizing filter between the other two at 45 degrees to both, some of the light now passes through all three polarizing sheets. We will now demonstrate optical activity in Karo syrup. A bottle of Karo syrup is placed between two polarizing filters. As the front polarizing filter is rotated, colors appear due to the optical activity of the Karo syrup. Three uniform cylinders of Karo syrup are now placed in overlapping positions between the polarizing filters. The front polarizing sheet is again rotated, showing areas of uniform color where the light has passed through the same thickness of Karo syrup. Some materials rotate the plane of polarization of polarized light when put under stress, an effect called photoelasticity. We'll place these acrylic figures between two polarizing filters to show the effect. When the acrylic is unstrained, the polarized light from the first filter is not rotated by the plastic, and the plastic is colorless. When we put stress on the plastic figure by tightening this screw, areas of high stress rotate the light from the first Polaroid, allowing only certain colors to pass through the second Polaroid. The plastic now appears colored at the stress points, with different colors corresponding to different levels of stress.
Optical activity and other polarization effects have been combined in an extremely clever and creative way by artist Austin Wood in an art form called the collage. A collage consists of a collage of optically active materials, and it is therefore viewed between two polarizing filters, one of which is attached to the front of the collage. The collage is placed on the front of this light box. The fluorescent light at the rear of the light box passes through a slowly rotating polarizing filter, then through the collage and the polarizing filter on the front of the collage. This example, called Swallowtail, shows the metamorphosis of a cocoon into a butterfly as the rear polarizing filter rotates.
Sample. Fixtures a system of three polarizing sheets, 1, 2, 3, in the path of initially unpolarized light. This unpolarized coming from here. The polarizing direction of the first sheet is parallel to the y-axis. This is the y-axis. This is the y-axis. That of the second sheet is 60 degrees counterclockwise from y-axis. Now, this is the y, the 60 degrees, the second piece. Okay. And that of the third sheet is parallel to the x-axis. What fraction of the initial intensity I0 here of the light emerges from the system, and how is that light polarized? We see this one, after the first one is half, because half was blocked. And from here to here, we use the law of Malus. The angle is 60. So I2 equal to I1 cosine 60 degrees squared. Okay. And this one, they have angle at 30 because it's 60 to 30. Okay. So I3 is I2 cosine 30 degrees squared. Okay. And then we put it together. We find I3 is about 9%, 9.4% of the original is almost nothing, okay? Only